All right, so today I'm going to talk about Set. This is a really fun card game if you haven't heard of it. It's a card game where you're trying to match sort of cards together to make sets and then try to see who out of your group of friends can make the most sets. So first to start, I want to explain what the cards look like. So on each card, there are 4 attributes, and in each attribute, there are like 3 sort of manifestations. And so for example, here are 4 cards. And we can see that like they differ in like color and also shape, fill, as well as
the number of symbols.
yes, number of symbols, thank you. Yeah, okay, so here we sort of have like a set of cards, and to make a set, you have to try to find cards that are either all different in each, or in one attribute, or all the same in an attribute. So more succinctly, you can say that like for a set of cards, you cannot say there are 2 of something. So for example here, like what is a set of cards?
I don't think there is one here. Oh, I see, these 3 over here.
Yeah, okay, so that's a set. And the reason why is because they're all different in each of the attributes. So they're all different colors, all different numbers, all different shapes, and all different fills. All right, okay. And another thing that we can like know about sets is that if I have 2 cards, then hopefully you can tell me like the unique 3rd card that fulfills the set. So like, for example, if I have these 2 cards, we know that they're both purple and they both have 1 on them. And since I can't say there are 2 purples or there are 2 1s, the last card has to also be purple and a 1. On the other hand, they have different fills and they're also different shapes. So I know that the last card also has to be a different shape. Otherwise I can say, oh, there are 2 of the same shape or 2 of the same fill. So then we know that last card has to be 1 purple, a diamond, and a solid.
Yeah.
Okay, and so we get this card. All right.
Now that's a set right there.
Exactly, this is a set. Yeah, and then so if we have these 2 cards, what should the 3rd card be?
Should be like 3, solid like lines, green squiggles, right? Like the ones with the weird fill.
Yeah. So this is a set because they're all different in all the attributes. Different colors, different shape, different number, and different fill. And then similarly for these, they're both similar in shape and fill, but different in all the other attributes. So we expect this to be our last card.
Yeah.
All right. Okay, so this is all fun and cool. One thing that I find especially fun about Set is that at the end of the game, once like sort of all of the decisions have sort of been made already, we already know who's going to win, but there's still sort of a fun competition that we can have.
Ron.
Okay, so suppose we play a game of Set, and like I've taken out a bunch of sets and I'm left with a bunch of cards left. And let's just say that these are the cards I'm left with. And I know that this is like a valid ending set because I just played this game with myself earlier. And so everything that's left here is our valid sets. Okay, so usually we play with like a grid of 12 cards, but I left out 1 on purpose. And I claim that we can figure out what this last card is.
How?
That's a great question. I'm going to show you. Okay, so I mean, at first this claim seems really outrageous because like we have 81 total cards, like 3 to the 4th cards, and like it seems pretty random what card this is. Like it could be any of the 81 perhaps, but actually it can only be 1. And so one way we can sort of try to think about this is to reduce the number of dimensions of our problem. So, okay, so maybe let's try it with 2 attributes. And in this case, we'll do shape and number.
Sure.
Okay, cool. So I'll just sort these in terms of by shape and also by number, and I don't care about the color or the fill. But then if I take like a set away, and we can see that this is a set because they have all different shapes and also all different numbers. We don't care about the fill or the color. And so now if I take away a card, it's a bit more difficult to figure out like which one should like which one it should be if we don't know what the set is. So one way that we can figure this out is by making this, like putting this on a grid and then trying to figure out what our sets sort of look like. Okay, so now let's plot our grid of set cards on a paper grid. Okay, and so we can have this sort of grid, and then we go 1, 2, and 3, 1, 2, and 3. Okay, so in each like point, I'm going to put a card. So this can like correspond to the number of cards, and this can correspond to shape. And so I'm assigning this to be oval, this is diamond, and this is squiggles. And then this is 1, 2, and 3, same as the numbers on the card. Okay, so here I'll have like the 1 of oval, this is 2 ovals. This is what our card grid translates to. And another thing that we can do with this grid is assign each card a coordinate. So if I tell you 1, 1, that like uniquely identifies this card for you, because I said 1 corresponds to ovals and also corresponds to the number of cards. So if I say like 1, 1, then this is equivalent to the 1 oval card. And then similarly, if I take like, for example, 2, 1, then I go 2 and then 1, and then this corresponds to the 2, then 1, and that corresponds to this 1 diamond card. Okay, cool. Now, if we want to think about sets, we know that in each set, every attribute has to be either the same or all different. And so if we just keep one attribute the same, it's easy to figure out what the sets are. It's just lines. So like we have horizontal lines, like this is a set, or this is a set, because they're all squiggles, but they're all different numbers. And this one is all 1, but all different shapes. Now, the all different sets like follow a different sort of line. So for example, this is an all different set because they have all different shapes, all different numbers. So this is a set, and similarly the other diagonal is also a set. But we have some more sets that are missing. And we can think about this as sort of like, if we move this bottom row up here, then we get a different diagonal. So this corresponds to like this card, then this card, then this card.
So it like wraps around.
Yeah, exactly. And so like sort of the boundaries we can call are periodic. And one way to think about this is like, if like we still want to describe this as like a line. And like a line in normal, I guess like Cartesian coordinates, you can say y equals mx plus b. And so in this case, we want to say like each point is some constant away from the previous point. And so like if I set this to be x, then this one should be like x plus r, where r is some constant. And then this one should be x plus 2r, so that it follows like some line. And in this case, we can solve for r. So since this has 1, 1, and this has 2, 3, then subtracting, we get r equals 1, 2. And so if we add that to this, then we get like 3, 5. But we don't want anything larger than 3. So we can sort of subtract 3 from 5, and then we get 3, 2. And then that points us directly to this card.
So how many sets can you form in this way? How many sets are there in this 2x2 grid?
Yeah, okay. So we have like all the lines, like all the horizontal and vertical lines. So that already gives us 6. And then we have 2 diagonals. So that gives us 8. And then we have like 2 of these funky sets. And so then that gives us a total of 10.
Yeah, because I'm thinking for every pair of cards, there's exactly one set that contains that pair.
Yeah.
But then also you might repeat, like for example, if a set has 3 cards, there's 3 different pairs there. So it's interesting to think about that.
Yeah, yes. This is indeed a problem that is very interesting to think about. And like one thing that mathematicians like to think about for a set is like, how many cards does it take for you to have no set in this card? Like what is the maximum number of cards where you cannot have a set. So like adding one more card guarantees that there exists at least one set. And this is called the cap set problem. And going back to this problem, so we have like this line of cards, and this is what describes a set. So an arbitrary set is given by this. One thing that we might observe about this line in particular is that if we add all of the coordinates together, so if I say like x plus r plus x plus 2r, that gives me 3x plus 3r. And in particular, we don't really care about what x and r are anymore, right? Because if we don't care about anything that's like greater than 3, then if I like mod out by 3, then this is equivalent to 0 mod 3. And that's equivalent to like this third row, we can say is 0 if we just set 3 to 0. But then we can also notice something like similar about the entire set of cards. For each card, I have like, let's say it's described by a vector x, where it's like x1, xn, where n is the number of attributes. Then if I want to sum over all of these cards, like add them all up together, this is equivalent to the sum where like x is like x1 then x2. Then we can sum over all the possibilities for x1, 2, and this can be 0 and has to be less than or equal to 2 if we set 3 to 0. And then we're summing over x1, x2. And then in this case, if we sum over x2 first, then we get x1 less than or equal to 2 of x1. But then if I add up all the x2s for one possible x1, then this is like 1 plus 2 plus 0. And so that gives me 3, which is equivalent to 0 mod 3. And so this becomes 0. And I can make a similar argument for the first coordinate. And so this becomes 0, 0. Okay, so this is interesting because the sum of our lines creates 0, and the sum of the entire deck is 0. So if I think about like taking a set as taking away one of these lines, then the entire sum of the remaining deck still is invariant. It's constant under this like taking away a set operation, because I'm just subtracting 0 from 0. Okay, so if we think about this in terms of our total, like our 11 original cards, we can sort of do a similar thing. So this is our 11 cards. Now we want to look at each attribute and see like what the sum is and try to make that sum to 0, because we know in each attribute our total cards should sum to 0, given that we've taken valid sets away. Okay, so first we can do it by fill. Then I can just set this to 0, this to 1, and this to 2.
And the total is 6.
Yeah, the total is 6. And so this tells me that like I should add another 0 to this. My card should have a value of 0 in this attribute. And so we know that the fill, in this case, is empty, because 6 is 0 mod 3. Okay, and another way you can think about this is like, I can take away like sets in only the color attribute, or only the fill attribute, because sets leave this like fill attribute sum invariant.
Yeah.
So I can take away this set, then this set, then this set, and I'm left with one more card. And so that has to be an empty card. And then I can do the same thing for the other ones. So now we can do it by number. So if I take away like set, 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 then I should have one more set left. And so it should be 1. And then we can do color. So, all right, there are a lot of reds, so you can put all the reds down here. The green's up here, purple's here. And now we have like, this is 0, this is 1, this is 2. And so we have 4 plus 2 times 2 is 4, so that's 8. And to make this 0 mod 3, you want to add a 1, and we assigned that purple. And so we should have color is purple.
It's like Alice Walker's book.
Yeah! Cool. And then finally, we are just missing shape. And so we can, and then if we take away this set, and then this set, then this set, we should have an all different set in shape. And so we're missing an oval one. So then our shape is oval. And lo and behold, if I take our last card, it is actually one empty purple oval. Wow. Okay, so now that you know this cool trick, next time you play set, you can challenge your friends to find the last remaining card and show them this neat modular arithmetic trick.